So hi everyone. Welcome to my presentation on Turing machines. We're going to be running through a mathematically-ish formal definition using some tuples and products and stuff. We're going to be talking about the transition function as both a function and a deterministic finite automata. Then we're going to be quickly brushing over our two-tape machines, and we'll be talking about fancy machines and how we can convert them to regular Turing machines and what that means for P, NP, and stuff. There is something up with the discrete finite automata, the DFA diagrams in the LaTeX. They get cropped off weirdly. Hopefully that shouldn't be a problem, and you can all understand approximately what's going on. So let's jump into it. This is the semi-formal definition of Turing machines that I find works for me quite well. Like everything, it's a tuple that's got, in this case, 5 parts. Part number 1 is an alphabet called sigma, and these are all the possible characters that could appear on the tape. So often it might be 0 and 1 and blank, or like A, B, C, D, but they'll always have a blank character that is generally really useful for all kinds of computation stuff. The second thing it will have is a return set. These are all the possible output values of the Turing machine. So this could be true and false, or 1 to 25, or 0 to 15 if your Turing machine, for example, converts binary to decimal for 4-bit inputs. And the convention is that when the return set R has only one element, that element is called halt. And the next thing that is needed to make a Turing machine is the set of states that the machine could be in. That's S. Every state, and these states could be stuff like currently wiping the tape, or process 7 part 1, but normally they have just number names, and they've all got to be unique because it's a set. And these are the nodes on the DFA when they come up in a second. Next element we need to talk about is the initial state. It is pretty simple. S0 is an element of S, and this is the state the Turing machine is in when you run it. So this is its starting state, and then the transition function, which we'll say in a second, moves from state to state, performing operations. So the transition function delta, it maps a state and a character. So that is the state the machine is currently in and the character under the head on the tape, to the new state, so the state that machine is going to end up in, the new character to write to the tape, and either left or right, which is the direction the head is going to move. Or instead of that output, it could just output a return value, so an element of this, the return set. And if we look at this definition in the bottom right, this is the domain and the range of the function. And we're using Cartesian products to represent pairs. So a pair of a state and a character would be the input. And what's this tape thing we've been talking about? You already know this, kind of. It's an infinite 1D array of characters from the Turing machine's alphabet, and there's a read-write head, which is basically just an index representing where the current character the transition function is going to operate on is. So it represents the character that is going to be read from and written to, and the movement direction, like increments or decrements it. So for example, by convention, a movement direction of left would decrement the head, basically. You can think of it as a little a little metal pointer running along the tape. You can think of a tape as a kind of bigger function. A Turing machine as a kind of bigger function. So it takes in a tape and it returns the end state of the tape, what the tape looks like after the computation is completed, as well as a return value from the return set. Or it might just hang. It might just have no output. And normally the input tape is an infinite string of blanks, apart from one word, which is the input word, and it's and the initial state position of the head is just the first character of the word. It's a nice convention, and it means that you can and if you stick to this convention, you can chain Turing machines together easier to have more complex computation stuff. So what is this transition function? What kind of mappings does it make? Well, something like if you're in state 1 and you read an A, then you'll write a B, move right, and then go to state 2 would be represented with this mapping below, as you can see. So it takes in a pair of a state and a character, that's 1 and A in this case, and it outputs a triple of a state, a character, and a movement direction, so that's 2, B, and right. So sigma of 1 and A is 2, B, and right. And instead of a triple, it could return just an element of R, so that's that invalid input there. And a little bit of really basic code that just takes a word made up of only A's and B's and wipes it, turns it all to blank, is sigma of 0 and blank is halt, sigma of 0 A and A is 0 blank and right, and sigma of 0 and B is 0 blank and right. This makes sense, I think. Is anyone stuck? Just give me a shout. I'm going through this quite quickly because I'm nervous, but it'll be fine. And as you can see, this function is looping into itself because it's remaining in state 0 and repeatedly replacing A's and B's with blanks and moving the head across the tape until it reaches a blank, which is, signals the infinite length of blanks at the end of the word. And that point, it's like, okay, we've reached the end of the word, we'll halt. But you might be more familiar with delta as a discrete finite automata, where each node is a state, and Turing machine operations happen on the transitions between states. Normally, because this is a deterministic finite automata, I don't know why I said discrete. Okay, that's weird. There's only one arrow going out of each node apart from read. So the read operation, you can have multiple read arrows going out of one node that represent the different values you could read from the Turing machine. So you might be in state 0 and either read A and go to state 1, or read B and go to state 2, etc. If you although you have a multiple arrows going out of a state, multiple transitions going out of a state, it isn't non-deterministic because only one of these arrows is definitely going to be traversed because that's the current character under the head of the tape, if that makes any sense. These two representations, they do represent the same underlying thing because you can kind of convert between them. So if we look on the bottom left, we've got an example of how you can how the mapping from state before and character before to state after, character after, and direction can be represented as a piece of a Turing machine. This wouldn't necessarily be a macro because it's not really about returning and stuff, but it's a piece that would fit into a larger Turing machine that would represent all the mappings that delta has. So in this case, the states X and Y are unique states that wouldn't appear in the Turing machine's DFA anywhere else. And if we have a look, mapping from delta to the elements of the return set is a little simpler. If a mapping returns, if a state returns something, it just means that when you enter that state, the Turing machine halts and outputs that value R. So if you're in state B and you state before and you read character before, then you move to state X and return R. That's the same as mapping the pair of state before and character before to R. Often it is a little easier to think about and visualize and work with DFAs, but the formal definition of delta with these Cartesian products is nice and definite and concise. So what happens if you take a Turing machine and add a second tape? It makes things a little easier. So you do have to change your definition of delta, as we can see at the top. It now also includes either 1 or 2 to say we're reading from state 1 or we're writing to state 2 and we're moving ahead on state 2. Each transition function application makes a change to one of the 2 tapes, and you can add more tapes to get better complexities. I think we saw an example in one of the lectures of this in action. So, for example, you can use the second tape to copy long strings from the first tape and store them for later usage, so you don't have to, modify and repeat stuff. And you can add any finite number of tapes, and you can get even better complexities if you're smart with designing your algorithms. And Shay is typing, exciting. A second tape would be really useful as a stack or a queue. You can use it to hold a bunch of different useful data structures. So this works for any number of tapes. You can add 50, 100, 150,000 tapes. And if you're smart with designing your algorithms, you can get ridiculously good complexities and constant factors. But no matter how many tapes you add, you can't take an exponential function or non-polynomial function or an NP function and turn it into a P program by adding more tapes. So no matter how many tapes you add, you can't breach the PNP barrier. So even if you had a 0.0012 to the n program, you couldn't add a second or third or 150th tape and write a new algorithm to turn that problem into a 100,000 n to the 50 or whatever. You couldn't turn it into a polynomial time algorithm. You can actually break this barrier if you use an infinite number of tapes, but it kind of defeats the point of a Turing machine to have infinite tapes or infinite states or infinite character inputs or infinite return sets, because Turing machines are supposed to be a basic mathematical model of real computation. And if you have an infinite computer and you say, hey, I can do this really useful algorithm on an infinite computer, you can't really use that algorithm in real life anymore because it only works on an infinite computer, or at least you've only proven it works on an infinite computer, because you can't build an infinite computer in real life. What a shame. So another kind of better upgraded bonus Turing machine is a fancy machine. So these guys have an extra set of characters, sigma f, and that are used in the internals of the machine, so they're not on the input tape and they're not really supposed to be on the final tape either. So sigma maps S Cartesian product sigma union sigma f to S Cartesian product sigma union sigma f, blah 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 blah. The point is that the set of characters available to be used in the transition function is now larger, and so you can express more complex ideas in the same amount of space and the same amount of time, because writing like a complex structure that is a single element of sigma f, for example, writing B and writing 0, they only take one operation each. So if you can represent more complex ideas with a better language, then you can then you can use the same. You can get better complexities because you're doing more complex stuff in the same amount of space and time. But no matter how fancy your machine is, you can't turn non-polynomial algorithm into a polynomial algorithm. It's just not possible, and it's very sad. This is kind of because you can convert fancy machines, and you can do the same with two-tape machines, but we don't really need it for our exams, and that's probably more complicated. You convert fancy machines to regular Turing machines, so, you know, how to... I don't know how to put that. Because you can convert fancy machines to Turing machines, they're kind of basically the same thing. So if you could do the algorithm in an NP algorithm in P on a fancy Turing machine, you could just convert it to a regular Turing machine, and then do it in P, at which point it's not an NP algorithm, and you've proved it's not an NP algorithm. But how would we convert a fancy Turing machine into a regular Turing machine? Well, there's a few steps. Firstly, you got to encode every character in the sort of combined language alphabet, except for the blank character, as a unique sequence of characters, and it's an n-long sequence of characters where n is the log base, the length of sigma except the blank of the length of sigma union sigma f except the blank, which is basically the smallest number of bits, except, like you could think of sigma as a number system almost, and it's the smallest number of digits required to represent all of sigma union sigma f. So for example, if sigma is just 0, 1 blank, then it would be how do you represent sigma union sigma f in binary. Blank is a special case. It's just represented as n blanks in a row. And then you've got to write a bunch of macros, yay, to replace all the read, write, move operations in the DFA, to operate on these new multi-character long encoded versions. So the move operation is you move n spaces to the left or to the right. That's two macros. The write operation, there is one write macro per element in sigma union sigma f, where it writes the character's encoding and then moves back to the start of the n block long string, so that it's ready for the next operation. They're all working from the same starting point for convenience. So for example, if you had like a triangle encoded as A, B, C, it would write an A, move to the right, write a B, move to the right, write a C, and then move back to the left twice, so you're back at the start, ready to have a proper move macro, move it 3 characters to the right, for example, to move on to the next encoded character. And then read, there is only one read macro, thank God, and it is a very complex macro, or at least in relation to the others. It is a it's a tree where it's basically a decision tree where you traverse through the multi-character encoded traverse through the encoding and eliminate options as you search for the encoded value. So for example, if you had that triangle encoded as ABC, you'd first read an A and you'd know, okay, whatever this encoding is starts with an A. Then you move on and read the next character, and you, for example, if you read a B, then you know it starts with a B, so now there's only a few options remaining. And move on to the third character. If you read a C, okay, there's only one option remaining now. Yes, at the end of the read-write macro, they should move back to the beginning of the encoded character. I actually forgot to put that moving back step on the read macro on the next page. Damn it. It's already too big and complex anyway. Cool. So it traverses down this tree to... and at the point when you've read both an A and a B and a C, there's only one option remaining, and that is triangle. So you can then return triangle. So the return set for this macro is sigma union sigma f, and so that your macro, if you replace read triangle with the macro of read triangle, then it basically means run the read macro, and if you return the triangle, move to that state. There are sigma without there's one leaf node for every character that's not blank, because blank's a little special because it's got its special encoding. There's one leaf node for every character in sigma union sigma f apart from blank, and the dimension of the tree, that's not the word, the arity of the tree is the number of elements in sigma. So if you had apart from blank, so if you had like four elements in sigma, like A, B, C, D, and also blank, it would be a quad tree. And let's have a look at some examples on the other side. So in our case, sigma is A, B, and blank, and F is C, D. So the number of elements in sigma without blank is just AB, so that's just 2. So this n is going to be log base 2 of something. And sigma union sigma f would be A, B, C, D, and blank. We ignore the blank, so that's just A, B, C, D, and that's 4 elements. So n is log base 2 of 4, or 2 characters required to encode this. That's just the formula that works for any sigma and any sigma f. But it's probably pretty obvious that if you have 4 characters and 2 of them are used in the encoding, then you'll need 2 bits. And so we've mapped A to AA, B to AB, C to BA, and D to BB, and as we said before, blank just maps to blank blank. Towards the top right, we can see the move right macro. So that's start in state 0, move to the right, and then move to the right again, and return. And there's an identical macro where the move rights are replaced with move lefts. On the bottom left, we have the macro for write A. And as you can tell, everything is just getting cut off really badly. I'm sorry about that. It starts in the start of the 2 character wide encoding. It writes an A, it moves 1 to the right, so it moves to the second character. It writes an A there as well because A maps to AA, and then it moves back to the start, ready for the next operation. And in the bottom right, we can see this ridiculous tree. And this is the read macro, apart from the fact that I keep forgetting to end the to have the move back to the start. So all these guys should have a move left before state 4 or move left. Oh look, I've got some state number overlaps. Okay, that's a problem. Whatever. This is a terrible diagram. Either way, so if you start in state 0 on the first element of the 2-bit encoding, and we read a blank, we know that the rest of it's a blank. We don't need to check the rest, so we can just say, we're done, return a blank. If we read an A, we narrow down our options to either A or B, because those are the 2 encodings that start with an A, so we can ignore the bottom half of the tree, move to the right to check the second character, and if it's an A, we know it's A, and if it's a B, we know it's B, because the encoding for A is AA, and the encoding for B is AB, and a similar case happens on the bottom right, so if you read a B first, then you know it's either C or D, because their encodings start with a B, and then BA maps to C, so if you read an A, you know that you're going to return a C. Well, move left and then return to C. And the same with BB and D. That's it. Basically, I've sped through this because I was in a rush. If you guys have any questions, feel free to message me or put them in the chat. Sorry for being a little fast. I hope everything made a bit of sense. Thank you so much for watching. I'm gonna stop the recording now, and then I get to say a funny. Cool, thank you.